Hello, this will be a demonstration of proposition 15 from book 4 of Euclid's Elements, which requires us to, in a given circle, inscribe an equilateral and equiangular hexagon. So just like proposition 411, where we had to inscribe an equilateral and equiangular pentagon, we are now attempting to inscribe an equilateral and equiangular hexagon, so a polygon that has not 5 sides but 6. We're thus given the circle A, B, C, D, E, F, so defined by 6 points. Counting's a bit hard. And the task at hand for us is in our given circle A, B, C, D, E, F to inscribe a regular hexagon, so an equilateral and equiangular hexagon. We begin by taking the center of the circle. We're going to call that center point G. We're going to do that by proposition 3(1). Next, we're going to have the diameter AGD, like so. And we do this by combination of postulate 1 and postulate 2. So we join AD, and then in the direction of point G, we produce it down to the point D. I believe these are actually the other way around. I believe D is on top. Okay. In any case, we have that diameter DGA. Next, with the center D and the distance DG, we're going to make another circle. We're going to call the circle EGCH. Like that. And E, C, and then let's just put H on top like that. And finally, we're going to join these straight lines EGB. So join EG and produce it down to B like so. And similarly, join CF and produce it down to F like so. And we end this by joining these straight lines AB, BC, CD, EF, and FA. Now what we're going to prove is that this hexagon A, B, C, D, E, F is equilateral and equiangular, and it has been inscribed in our given circle A, B, C, D, E. We begin proving this by noting that GE must be equal to GD because they're both radii of the same circle, and being radii of the same circle, definition 115 tells us that they are equal. Furthermore, we also know that DE must be equal to GG because these are both in the same circle, not A, B, C, D, E, F, but DE and DG are both part of the circle EGC. So they're also equal to each other, which means that GE is equal to ED. So GE right here is equal to ED right there. Which means that the whole triangle DEG is equilateral because all of its sides are equal to each other. In definition 120, that's the definition of an equilateral triangle. This triangle DEG is evidently equilateral. Okay, now being equilateral, we know that it is also equiangular. We know this by using proposition 1(5) and noting that the angle DEG must be equal to the angle EDG. Right, because an equilateral triangle is also isosceles for that matter, right? It has 2 sides that are equal. And so the angles which subtend equal sides are, the angles which are subtended by equal sides are also equal. That's proposition 1(5). And so the angle EDG is equal to the angle DEG. For the same proposition 1(5), we can note that the angle DEG is also equal to the angle DGE, which means that the angle DGE is equal to the angle EDG, and thus the triangle DEG is not only equilateral, it is also equiangular. And we know that the sum of all of these angles, EDG, DEG, and EGD, right, the sum of all these have to be 2 right angles, right? That's proposition 132, that the interior angles of any triangle add up to 2 right angles. And so if the whole sum of these 3 angles add up to 2 right angles, and each of these angles is equal to each other, we know that each angle must be a third of 2 right angles so that they can both be equal to each other, and that the 3 of them added together can equal 2 right angles, because obviously 3 1/3 just adds up to the whole. So each angle here is equal to 1/3 of two right angles. Namely, the angle EDG is equal, or EGD, my bad. The angle EGD is equal to 1/3 of two right angles. Now we can prove in a similar way that the angle DGC right here is also equal to 1/3 of two right angles. And we note that, excuse me, DGC. I did it again. Okay, I mean, DGC is equal to 1/3 of two right angles, but that's not important. What's important that both the angles EGD and DGC are equal to 1/3 of two right angles. And we know that when we have one straight line falling upon another straight line, the angles that are made add up to two right angles. That's proposition 113. And so the angle the angle CBG, which is right here, plus the angle CGE, those two angles added together must be two right angles. And the angle CGE is composed of 1/3 of two right angles. And so if the whole thing is also to add up to two right angles, and we have 1/3 of two right angles, then the remaining angle CGB must also be equal to 1/3 of two right angles. That's just common notion 3. It looks a little funky because everything's equal, but nonetheless it is common notion 3, right? All three of these angles add up to two right angles, and we have two of them which are equal to 1/3 of that sum, so the remaining angle must be the missing third. So the angle CGB is also equal to 1/3 of two right angles. And we note that these angles here, that all three of these angles, which we have just shown to be equal to 1/3 of two right angles, they have vertical angles. And we know by proposition 115 that vertical angles are equal. And so all of these angles here, their vertical angles are also equal to 1/3 of two right angles, which means that the angle AGB, which is equal to the angle EGD, is equal to 1/3 of two right angles. The angle FGA, which is equal to the angle DGC, is also equal to 1/3 of two right angles. And finally, the angle EGF, which is equal to the angle CGB, is equal to 1/3 of two right angles. So all 6 of these angles right here around the center of the circle are not only all equal to 1/3 of two right angles, but they're all equal to the same thing, so they're equal to each other. That's common notion 1. So all 6 of these angles right here at G are equal to each other. And we know by proposition 326 that equal angles stand on equal arcs. And so these 6 equal angles here must stand on 6 equal arcs, which means that the arc AB is equal to the arc BC, which is equal to the arc CD, is equal to the arc DE, is equal to the arc EF, is equal to the arc FA, right? Because we have equal angles standing upon all of these arcs, and so by proposition 326, the arcs on which equal angles stand are equal to each other. And furthermore, we know that equal arcs are cut off by equal straight lines. That's proposition 329. And so not only are these 6 arcs equal to each other, but the chords which cut them off are also equal to each other. So we can say that the straight line AB is equal to the straight line BC, is equal to the straight line CD, is equal to the straight line DE, is equal to the straight line EF, is equal to the straight line FA. Which means that our whole hexagon here, A, B, C, D, E, F, all 6 of its sides are equal to each other. And so the whole hexagon A, B, C, D, E, F is equilateral. It has thus been proven that it is equilateral. And next, we're going to prove that it's equiangular. We begin this by noting that the arc FA has been shown to be equal to the arc ED, right? That was step 6. And so if we add the same arc to both, we know that the sums that we get will also be equal to each other. That's common notion 2. And so if we add the arc ABCD to both of these, we know that the arc FABCD is equal to the arc EDCBA, So those two arcs are equal to each other by common notion 2. And we know by proposition 327 that upon equal arcs stand equal angles, which means that the angles which stand upon these equal arcs are equal to each other. And so we can say that the angle AFE, right here, which stands on the arc EDCBA, is equal to the angle, DEF, which stands on the arc FABCD. So again, the angle AFE is equal to the angle DEF. We can prove in a similar way that the remaining angles of our hexagon ABCDEF, all 6 of these angles are equal to each other. And so this hexagon ABCDEF has not only been shown to be equilateral, it has also been shown to be equiangular, and it has clearly been inscribed within our given circle ABCDEF, which means we have done that which we set out to accomplish. In our given circle ABCDEF, the equilateral and equiangular hexagon ABCDEF has been inscribed QEF. Now, there's a porism attached to this proposition. The first of which is that we had shown in step 2 that GE is equal to ED, and ED is the side of one of our hexagons, and GE is the radius of our circle, which means that the radius of a circle is equal to the side of the regular hexagon inscribed in it. Or, in other words, that if you have a regular hexagon, if you have an equilateral and equiangular hexagon, and you circumscribe a circle around it, the radius of the circumcircle will equal the side of the hexagon. Now, Euclid does not go on to show, as he did with the pentagon, how to circumscribe a regular hexagon around a given circle. And he doesn't go through how to inscribe a circle within a regular hexagon or how to circumscribe a circle about a regular hexagon. But he says that doing these 3 tasks is very similar. In fact, it is very similar. It's not identical because, you're working with one more side. But the method of circumscribing a hexagon is going to be the same as proposition 412, which means that if we draw to our given circle ABCDEF, tangent lines at all the vertices of our regular hexagon, so we draw a tangent at A, B, C, D, E, and F, then these 6 tangent lines will form a regular hexagon. We can prove this just as we did in proposition 412. So Euclid doesn't go through because it's the same old stuff. Now, again, in the case of beginning with the regular hexagon and either inscribing or circumscribing a circle about it, doing these constructions works very similarly to propositions 413 and 414, so Euclid does not go through them for the same reason. It's much of the same old stuff. And so, that being the end of the porism here, and I having nothing to say about this proposition that has not already been said, I'm going to end the video here and move on to 416.